Now friends, we will discuss about another special type of flow or property which is exhibited by various materials, which is called as viscoelasticity. As the name indicates, it is viscosity plus elasticity. Now the first question comes that we are talking about all fluids and liquids. So how does elasticity comes into play? Now we are dealing with suspensions, we are dealing with semi-solid dosage forms which have a solid component. And because of that solid component, in some formulations, elasticity along with viscosity plays important part. If we take an example such that semi-solids, creams, ointments, paste, magmas and other materials such as amorphous and semi-crystalline solutions, thickened polymeric solutions, carbopol solutions, all these materials because of higher solid content exhibit viscoelasticity. Means the liquid component has tendency to exhibit viscous properties, whereas the solid component has elastic properties. But when both of them are mixed together to form a semi-solid dosage form, then viscous properties influences elasticity and elastic properties influences viscosity, which we will show in the video ahead. Now, if we see the viscoelastic materials, they are always a combination of liquids and solids. Viscoelasticity is a molecular rearrangement. Basically, the polymers are formed because of the reaction. So monomers are converted into polymers. These are long chain, and usually polymers are combination of liquid and solids. So these polymers also exhibit viscoelasticity. Now, as I told you, viscoelasticity is a molecular rearrangement. So when stress is applied, first of all, there is no external change, but this stress causes rearrangement. Now this rearrangement is reversible because it has elastic component. Material again is like a solid, but internally it is changing and it can again come back to its original position if stress stops here. But if we keep on applying more stress, then viscous comes into play. The physical property of the material changes. Suddenly the polymers starts to flow and viscous properties comes into play. At this time, if we stop the stress, then some part it regains, means it turns to be semi-solids because of the elastic properties, but some change are permanent due to viscous properties. So all the viscoelastic materials have three things in them. One is they have hysteresis in the curve. This means their graph is not single line, there is a curve in the graph. The second thing is they have creep. Now what is creep? Creep is time dependent change in strain at constant stress, whereas stress relaxation is time dependent change in stress at constant strain. So we will define both these terms later. See, now when force is applied, see what is creep? Time dependent change in strain at constant stress. When stress is applied and we stop the stress, the molecular rearrangement occurs. This molecular rearrangement is defined as creep. Whereas because of this molecular rearrangement, there is back strain developed. This back strain is refers to as stress relaxation, and because of these two, the curve is not a single line, it is a area bound curve called as hysteresis. Now creep curve is the property of viscoelastic material. Creep curve is not the graph between stress and strain, it is graph between creep modulus. Creep modulus means changing creep on constant stress along with time. Fine. So the graph between changing creep or creep modulus along with time is referred to as creep curve. Now if we see different portions, so this is the creep curve for viscoelastic material. If we see different portion, point A to B refers to elastic change, then point B to C, since stress is increasing. So on application of stress, first of all there is rearrangement, which is elastic in nature, represented by AB. Then there is viscoelastic changes. So elastic as well as influenced by viscosity, which is shown by this curve B to C. Then there is a linear portion which indicates only viscous changes. This is the stage now the bonds start to break between the polymer and its physical properties begin to change. When stress stopped here, then point D to E is rearrangement, which is similar to the elastic deformation. So here some part of the material regain its original position, try to regain its original position, and this belongs to this much elasticity. So these areas are same. This is deformation, this is restoration of deformation. But after certain level, after point E, then because of viscous deformation, the change become permanent, and ultimately the physical property of the material acquires a new physical property. So this is creep curve for viscoelastic material. Now, since viscoelastic materials consist of both components viscosity and elasticity, so several models have been used to describe viscoelasticity. These are mathematical models which are used to describe viscoelasticity. On application of these mathematical models, we are able to tell what is the behavior of the material, what is the use of the polymer, how it can be used in a pharmaceutical application. Now there are several models, two of which are more important. The first one is Maxwell model. The second one is Kelvin-Voigt's element. Third one is standard linear solid model, and the fourth one is Viscoelastic model. Now, out of these two models, Maxwell and Kelvin-Voigt's model are very important. Now, since we have viscous and elastic components, therefore all the mathematical model also consists of one viscous component and one elastic component. Viscous component is referred to by dashpot and a piston in which liquid which is to be tested is poured. So this dashpot with a piston along with a fluid resembles viscous properties. When stress is applied, the movement of the piston is regulated by the viscous force of the material. Whereas elasticity is referred to or is exhibited by spring. So spring is used for elasticity and dashpot is used for viscous material. In Maxwell element, spring and dashpot are arranged in series. So in Maxwell element, they are arranged in series. So when force is applied, first of all, contraction of a spring takes place. Because of that contraction, there is movement of the piston also. When force is released, the spring comes back to its original position. The piston does not move because there is no back force, and the slight movement of the piston is because spring is again relaxing to its original position. So Maxwell elements are used to characterize the flow behavior of viscoelastic materials, but they are not good models. They does not give any information about creep. They only give information about stress relaxation. So we use more valid model, which is Kelvin-Voigt's element. Now in Kelvin-Voigt's element, both of them are arranged in series. In parallel. So when force is applied, spring does not compress totally. The compression of the spring depends upon the viscosity of the fluid, because this viscous drag controls the movement of the piston inside the fluid. So spring does not compress completely. When force is applied, the compression of a spring depends upon the movement of the piston, or you can say the viscosity of the fluid. If fluid has lower viscosity, spring will compress more, piston will move down. If it is thick, movement is slow, spring is less compressed. When force is removed, similarly, spring relaxes, but the relaxation of spring is regulated by the viscosity of the liquid. If material is thick or it thickens on application of force, then it does not allow spring to relax because it will hold the piston. But if it becomes less viscous, then it will allow easily, and the changes, the movements will help us to determine what is the relationship between viscosity and elasticity, jointly called as viscoelasticity. So if in this case, this is Kelvin-Boyd's element, it is used to determine creep very handsomely. So this model is good for creep determination. However, it lacks information on stress relaxation. But I'll tell you, creep is more important property for viscoelastic materials. Now comes other models, Vicard and standard linear model. They are modified form of these models. However, they are used for advanced polymers. In case of standard linear solid model, a spring is attached here and this is like this relation. Now in case of Vicard model, many such components are attached here. So this advanced system will give us how to characterize the advanced or complex polymer, because complex polymer has complex viscoelasticity. So these advanced models are used to characterize their flow behavior, and these polymers are used in development of artificial pancreas, they are used in development of drug delivery systems and various other dosage forms.